All right, good morning, everybody. Let's get started. It's 10 o'clock. So, first off, thank you for joining us again this morning. If you've been joining us every week, thanks for coming back. So, first off, if you can mute your phones or mute your connection, that will help a lot. So, let's get started. So, the topic this week is the importance of proper commissioning of a parallel positioning system. So, we'll start with methods of load control, just some basics. So, the first and most basic method of load control is on-off control. So with on-off control, a large output is simply turned on and off as needed to maintain a set point over the course of time. So this would be something like your thermostat at home. With on-off control, there can be a lot of stress on the equipment through the on and off cycles. And if you graph the set point change against the actual, you will see that the graph oscillates up and down around the set point as it's turning on and off. So the end result is that the average of the oscillation satisfies the set point, but the choice you have to make is whether you want to have fewer cycles with a larger hysteresis away from the set point, or if you want to have tighter control, which will result in more cycles. But either way, the average is going to satisfy the set point. So next you have proportional control, and this is an upgrade to on-off control. And proportional control requires that the output can be modulated, and it'll proportionately adjust the output as the actual value gets closer to the set point. So these controls could often be referred to as slide wire controls, and they commonly use a 0 to 135 ohm resistance wired to a modulating motor to adjust the output. Proportional control can still be used with modern 4 to 20 milliamp controlled motors as well as parallel positioning systems if the load is steady. And variable loads can present a challenge for a proportional control system, as there is no way to compensate when the load shifts and the output is too high or too low, which results in poor control. And in this case, the output would be a little more similar to that of an on-off control because it might start to oscillate. So PID control is the third type, and PID control adds additional terms to proportional control to address two deficiencies. First, the term called integral is applied that measures the error, which is the difference between the set point and the actual value, and it makes adjustments to the output. A second term called derivative monitors the rate of change and can make adjustments based on the instantaneous slope of that rate of change. So you can think of the proportional term as the present, integral as the past, where you add to the output based on the past output, and derivative as the future, where you'll make adjustments assuming the current rate of change will last forever. The amount and intensity of each of these terms is adjusted with a process called tuning, and that's what determines how well the PID algorithm is going to work and calculate. So either the integral or derivative contributions can actually be disabled if not needed, which could even make it proportional control again. So some of the requirements for PID to work is, first of all, feedback. PID control requires feedback in order to work. The feedback is the measurement of the actual value that is subtracted from the set point to find the error. The proportional and integral are calculated from the error, but as we mentioned, the derivative is calculated only from the rate of change of the feedback. But without feedback, the error would always be at the maximum, which means that you would be the furthest away from your set point, and so your output would always be at the maximum as well. So this little diagram is showing PID loop, and the requirement of feedback is what is referred to as closed loop control, because it is closing the loop, as you can see in the diagram. You have the set point going in, calculating the error, goes through the proportional, integral, and derivative calculations, adds those together, sends the output into the process, and then it comes back into in the closed loop back into the beginning of the process. So quality of feedback is important. The feedback simply reads the actual process value, which is mechanically linking the output of the PID control back into the input via the process. It is actually decoupled from the process, or it is actually decoupled by the process. And that decoupling is the reason why there is a delay between the output changing and seeing a change in feedback. As much as is possible, the feedback should reflect that what the PID algorithm is requesting is being properly deployed. So a PID request of 50% should mean that half of the output is being put into the process, and the expected amount of return should eventually be seen in the actual value. How well this works in practice determines the quality of the feedback. If the requested output percentages are not even close to the corresponding outputs being put into the process, the quality of the feedback is poor. PID controls need to be tuned. They rarely will work well out of the box. There may be good starting points, but every installation will need to be monitored, and each of the 3 terms will have to be adjusted as necessary for the individual process. So dynamic loads, ones that change often, can be the trickiest to tune. Another issue that makes a PID loop hard to tune is when there's poor quality feedback, as we just went over. But PID tuning is a very complex subject, and there are many methods and strategies used. PID tuning and PID itself is a whole nother topic. So theoretical considerations with PID. In theory, the output should be nothing when the PID algorithm is requesting 0%. In other words, the equipment would turn off. With proportional only control, this is the biggest drawback, since the output would end up being 0% right when you get to the set point, meaning you can get infinitely closer and closer to the set point, but you can never reach it. Imagine a drone using proportional control to rise. If the drone was at 100% power as it rose, but as it was getting to the height it needed to be, it would go less and less. When finally it went to 0%, it would just fall. So you can see that wouldn't always work properly. It would never get to the height it was supposed to get to, because it would stop, the rotor would stop turning and it would fall. But that is just theoretical, however, since the actual minimum output is often greater than 0, or it is externally influenced. Examples of the external influence would be the effect of gravity or momentum on a cruise control system, which of course can be counteracted with brakes, but assuming we didn't do that, the gravity or momentum would override the fact that the output was actually 0 and it would continue rolling. Or the size of low fire on a boiler is another example. Even though the output is requested to be 0, low fire is not actually 0, so you still have output. In fact, if the load on a boiler is steady, using proportional only control can work without a lot of cycles due to the fact that the output during low fire is actually greater than 0. So the importance of proper commissioning. As just mentioned, tuning can be difficult if the output is not linear. The output is the direct result of the commissioning process. During commissioning, the goal is to have the output of the burner follow a linear curve from low to high fire so that the PID can calculate the output as well as possible. This makes the PID loop easier to tune, which in turn makes the process operate better. It is also important to ensure that you can get the maximum turn down available when commissioning. This will not only help to reduce cycling, but will also allow finer control by making a wider band of power output available to the process. So the first steps to proper commissioning is the first thing to do is to make sure that the fuel delivery system is capable of reaching both the minimum and maximum output required. So for a natural gas system, this means checking that the regulator and all the regulator parts are able to deliver the right amount of gas. And the same concept would apply for any other fuel as well. Make sure that you can deliver the right amount of fuel for the process. So just start by making sure that's the case. Next, you want to find a way to isolate the fuel flow so you can measure it. And this is important since it is how you will measure the output during commissioning. And you do have several options. In order of preference, the best way to do it is to simply use a fuel flow meter, which is going to be a dedicated way to read the fuel flow. This is by far the best option since it allows you to measure the fuel flow continuously throughout commissioning, as well as to monitor periodically as time goes on. So you can continuously monitor the fuel flow anytime you want to. Second option is to clock the meter, the gas meter, for example, to calculate the output. This would require either a dedicated meter or the ability to isolate the equipment you're testing so that it's the only equipment using the meter so that you can clock it. And the last option would be to use a published burner head pressure to determine the output. And since these are theoretically calculated also, there may be inaccuracies, but it is better to do this than to not have anything else you can use to try to measure the fuel flow. So on the FireEye website at fireeye.com, we have a spreadsheet designed to help with commissioning any Nexus system, and it can be found in the NXF 4000 section under the heading Service Guide. And the worksheet is called Nexus Commissioning Worksheet for Gas Fuels, and it works with either the 4000 or 6000 series controls. It is a Microsoft Excel macro-enabled workbook, and so you download it on your PC and you can use it as a guide through the commissioning process. So we'll go through that in the next slides. So the worksheet is configured to calculate 10 points, which can take the guesswork of how many points to configure, so it gives you a nice framework to work with while you're commissioning. So the first thing when you use the worksheet, since it's macro enabled, you do have to enable the macros, and the banner is at the top, and it's this little yellow banner, so it could be hard to see. It's not terribly big. It's not as big as it is here. So you want to click enable. The macros are what it uses to make its calculations. So at the beginning, we have a section where you can fill out site information. So the worksheet can be saved or printed, and it can be a way to keep commissioning records. So that's why we have this section. There's also a section at the end called Other Notes, and you can use that as well. So you have some areas to add some additional information. So the first 4 steps in the worksheet just require that the servo and VFD positions are recorded. And this is simply for record keeping. This isn't part of the final curve, but you do have your standby positions, your purge positions, and your ignition positions that you're going to want to record. You also can have up to 8 servos. You can see there's 8 boxes, but only 3 of them have names. You can actually change these names or delete these names as needed in the standby position section. If you change the name of AR servo, for example, to something else, it would change in all of the other positions. So this is where you would set the names. So next you're going to, step 5 is the most important step in the process because this is where we're going to set our high fire rate. Although we're at 0.3, which is normally the first point in automatic, normally what you would set for low fire, you actually want to set your high fire rate here. So the first thing you're going to want to do is carefully drive the gas servo to wherever you want it positioned for high fire. So we're not going to save 0.3 as high fire. We're just going to use the fact that we're at 0.3 to drive it to the high fire position to record the servo positions, to set the meter where we want it, clock the meter and set it where we want it, the regulator where we want it, and then we're going to go back and actually set low fire before we save it. So in this step, we're going to go to the high fire position, and so we're going to have to pay attention to the analyzer during this step to keep the combustion on the lean side as the servos and VFD are moved. And we're going to want to check the burner head pressure at the high fire position. We're also going to enter the rated output and BTU value of the natural gas on this step. But really all this step is for is to get the burner to the high fire position temporarily, to record the servo positions, to set the pressure on your gas regulator so you know that high fire is where you need it to be after you clock it or you look at your fuel flow meter. And then we're going to just record that. So the next step, before we get to the next step, one of the issues with that step is a lack of load for high fire. And that's a very real issue at this point, is that there may not be enough load on the boiler or burner to get to high fire long enough to set the regulator pressure and record the positions. And this is actually going to be the case a lot of the time. So one strategy that can be used is you can set up a rough curve with a few points. You can actually save 0.3 and go to 0.4 and just make a temporary curve just to get to the high fire position so that you can set your regulator, make sure your high fire is where you want it, note the servo positions, and then basically start over. And so if you do save points when you go back to start again, the Nexus control will go back to the positions that you were at the last time before. You didn't finish commissioning, but the positions were saved, so it'll remember those positions as you step through the curve again. And once the Nexus control has been commissioned, entering commissioning mode again just walks through the existing points, but allows you to make changes and confirm the settings. The standby, purge, and ignition positions will be remembered, and you don't have to change those. And you simply begin making adjustments at P3 and continue adding points as needed. So going back to the worksheet, now that we've completed steps 1, 2, 3, 4, and 5, step 6 is to actually set the low fire position for 0.3. So we've been at 0.3 this whole time. We temporarily went to high fire, set our regulator. Now we're going back and actually setting low fire. So after the regulator has been set and the low fire positions have been recorded, the control can be shut off and commissioning mode started again, or you can drive it back to low fire. The first 3 points will be remembered, allowing you commissioning up to P3 to begin fairly quickly. Once at P3 again, set the low fire positions as you normally would, making sure to pay attention to the turn down. Read the fuel flow meter or clock the meter at low fire as well to ensure that the turn down requirement is being met. And this is very important. So if your boiler is supposed to be 8-to-1 as we wrote here, you're going to want to make sure that your turn down, that your low fire is 8 times less. So you're going to want to clock the meter again or read the fuel flow meter. So step 7, this is where we set our curve points. Now once you enter in your servo positions for low fire and high fire, it's going to fill out this target numbers on this curve for you. So it's going to have points 4 through 12, and it's going to give you targets for air, gas, and VFD. So using the target positions as a guide, you want to set the servos and VFD for each point. So you always want to use an analyzer and make sure that combustion is safe while traveling to the point to each position. And keep in mind that this is just a guideline, so you don't want to just go straight to these points without doing it safely. So first thing, you want to set the VFD exactly as it's shown so that its travel will be a linear path. The VFD is the least critical of these. As long as you're following your linear path, you're going to be fine. Next, you want to set the gas servo to produce either the target burner head, if you don't have any way to read the fuel flow, or you actually can read the fuel flow and set the gas servo so that your fuel flow reading is exact. And that's what keeps the output linear, is that the fuel is linear. And then the last step is you trim the air servo however much is needed to get the O2 readings you desire. So then you record the actual positions that you set into the green column, the darker green column. And note that you don't actually have to clock the meter at each intermediate position. We just clock it at low and high, and we use the burner head pressure for the intermediate points to make sure we stay on our curve. So note that for each servo, there is a butterfly checkbox on the worksheet. And checking this changes the target values based upon the flow dynamics of a butterfly valve. So the output follows a polynomial curve on a butterfly valve rather than a linear curve. So you'll notice the differences when the box is checked versus not checked, and it's shown here. The main point to know is that a butterfly valve doesn't deliver half of the flow until a point somewhere between 60 and 70% of the travel has been reached. So it's going to give you slightly different numbers when you click the butterfly option. But keep in mind that these values are just approximations. The actual servo position is set to achieve the desired burner head pressure, flow rate, or combustion numbers. So don't just follow the target, it's just a guideline. So the worksheet, once you're finished, is designed to print neatly on 2 pages, so you can print it as a PDF. It'll print, or print it on paper. It'll print in 2 pages like this. So caution, some important points to hammer home. We've already mentioned them, but maybe not enough times. So always use a combustion analyzer when moving servos and VFD positions with a fuel valve open. The combustion numbers are more important than the target positions. Try to get high fire as early in the process as possible so the regulator can be set for the high fire rate. Even if it's hard, if you don't set high fire and you get through the whole curve and then you have to adjust the regulator when you get to high fire because you're not anywhere close to your output, then it's going to mess up all the rest of the curve before it. So it really is in your best interest to try to get the regulator set for the high fire rate as soon as possible. And lastly, adjust the fuel servo to achieve the rate shown on the fuel flow meter or achieve the burner head pressure for an intermediate point. But after that, only adjust the air servo to change the combustion numbers. If you start changing the fuel servo as well, you're going to change your fuel output, and then your output curve will not be linear anymore. And always adjust the VFD in a linear manner so it just follows a straight line, just to keep things simple. So while PID control may not be the perfect solution due to turn down limitations, it works quite well in most burner applications when the burner is commissioned properly. It is when commissioning is done with no reference to the gas input that problems can develop, and the PID control itself will usually be blamed for that. If the commissioning is not done well in the first place, there is no amount of PID control tuning that will ever make the burner run well. Even if it can be made to run reasonably well, it will be less efficient overall and will cost more to operate in the long run. The easiest option for proper commissioning is to use a fuel flow meter as a commissioning tool, or to permanently install one on for each burner. For gas fuels, inline fuel flow meters often only need a single tapping and a straight run of pipe to install, and this tapping can be specified during installation. Upon commissioning, you simply isolate the gas line, remove the plug, and install the meter. Remove and replug the tapping when you're done. So using a fuel flow meter can save a ton of time during commissioning by making the process more structured and repeatable. And your effort is reflected in the result. The ability to control the process will only be as good as the effort made during commissioning, and that's true for most things. So remember that for most endeavors, what you get out of something depends upon what you put in. So these efforts will also ensure that the customer is getting what they pay for, but getting the most out of their new equipment, and I think that's the most important part. So thank you guys for tuning in. I will stay for a few minutes. If anybody wants to ask a question, you can type it in the chat, and I can answer that if you don't. Thanks for joining, and hopefully we see you the next time.